Okay. Okay. Now, I will tell you something about a main advantage of this two complement number system. Suppose you are adding, like in digital systems, digital filters and all that, you add, like you carry out filtering operation. So, you find out yn is a convolution sum like H0 x n plus h1 x n minus 1 and dot 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 up to maybe h. So, okay, this is one term, this is another term, another term you are adding. You do multiplication and then you are adding. Now, if whenever you add two numbers, say A and B, if the resulting value is within the range, what is the range of the two complement system of W bit system? On the positive side, it is this upper half and lower half is -1. This is the range and 0 in between. If the sum is lying within this range, then there is no problem. There won't be any overflow. W bits are good enough to represent the resulting one uniquely. But if the resulting sum has an overflow, then one bit will go. When you add, one bit from the most significant bit will go further to the left and that will be lost. So, whatever W bit result you get, that will be wrong. So, overflow is a problem. You need to check overflow and then make corrections accordingly. This is a big problem in general in addition. Now, here what happens, suppose you are carrying out a summation like this and it is somehow told that final summation, that is this result, is within this range for W bit representation within this range. So, this is fine. So, if you give me W bit, you can always represent this nicely without any overflow. Suppose this is given to you, but the way you are calculating so many additions. So, it is quite possible that some intermediate sums, because you always take two at a time as an adder. The adder is a 2 input 1 output device, it can take only this adder for that matter, it can take only 2 fellows as input and give 1 fellow as output. Again, that you take add with another fellow and like that. So many intermediate summations, it is quite possible that even if the final result somehow you guarantee to lie within this range, intermediate summations you do not have any control, maybe they will lead to overflow. Ultimately, somebody will cancel out something and finally result will come back in this range, but some intermediate summations can give rise to some overflow. If that overflow is not checked, there will be error. There lies the advantage of two complement system, that if you follow two complement number system, even if some intermediate sum here on this side has an overflow, there is a theorem that states that you just ignore that overflow as it did not occur. Whatever result you are getting, that may appear to be wrong, but please move with that result. Carry on with the entire summation. Eventually, the result that we will get, that will be the correct yn. There is a theorem, it requires advanced mathematics, but that is the beauty of this two complement number system. That is, whenever you are adding too many numbers, if the final number is guaranteed to lie between -1 to this 1 minus 2 to the power minus w minus 1, that is in the range of a W bit number, if that is guaranteed, then even if there are intermediate overflows, then you are doing so many additions, even if some intermediate overflows in some intermediate sums, you can just ignore them and carry on with your summation as it is. Do not have to worry, final result will be as it is, will be correct. This is a property of two complement number system, which is very useful in digital signal processing, because here you come across convolution sums where too many things will be added, or you do a transform, discrete cosine transform or DFT, where again in the summation you have too many things to be added and like that. Okay. You are guaranteed to have a overflow free operation result. This is the main advantage. Now, we consider multiplication. Multiplication of two numbers in two complement form. Okay. Suppose you are given A which is a w minus 1 dot a w minus 2 dot. Okay. You know the decimal value under 2's complement system. I ignore this intermediate thing, a 1 to the power. Similarly, here okay. Now, digital multiplier means you develop a circuit, develop some digital hardware where one input you give as A, W, so there is a bus, W bit bus that carries all the bits of A. Similarly, another W bit bus that goes in that carries all the bit of B. And then you do some processing inside, the result should be such, if you call it C, which is actually A B, A dot B, A and I want the product. This should be a W bit number, this should be a number, some word whose decimal value should be equal to product of the decimal of A into product of this. That is, this C should be such that C of decimal, I want to generate as output C, so that the decimal value of C should be A by D times B by D. Then that hardware will be called a digital multiplier. That is, it takes A W bit numbers, it takes B W bit numbers, does some kind of processing, generates an output C, so that the decimal value of that C under 2's complement system will be nothing but product of decimal A and decimal B. If you can do that, then that is called a digital multiplier. Okay, digital multiplier. So, that is what we will try to work out. We will follow what is called Hodnor's rule. A by D into B by D. B by D I write like this, and this entire thing to be multiplied by A by D. So, A by D times this, which is also you can write as minus of A by D times this decimal thing. Whenever you write this expression, everybody to be treated as a decimal digit. The value remains same. If it is originally binary 1, now it is 1, decimal 1. If it is originally binary 0, now decimal 0. But it is a decimal digit now, that is why I can put minus here, I can multiply by 2 inverse and all those. This we cannot do when it is purely binary bit. Then operations are very limited, 1 plus 1 is 0 with carry 1, or AND gate, all those things. You cannot write like this. So, product will be the decimal value of A by D into the entire decimal expression, which is A by D times this. I take the minus with A by D, this. Then 2 inverse I take common. So, A by D times this. Then I had 2 to the power minus 2, 2 to the power minus 3. So, again I take another 2 inverse common. So, again A by D times next bit. Again take 2 inverse common and dot 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 dot. Finally, you will have 2 inverse common A by D times B, this one 1, and again just last 2 inverse times A by D times B 0. Okay, you can put this also under a bracket, but no need, dot 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 this. So, it is a nested function, and this rule is called, this is a chain rule called Hodnor's rule. That is function within a function, it is nested. 2 inverse A by D times B W minus 2 plus again 2 inverse A by D times B W minus 3 plus again 2 inverse and so on and so forth, similar thing. Okay. Now, to show how this can be used to build up a digital multiplier, we will take an example of 4-bit numbers, that is W will take to be 4 as an example. So, it will be A3, A2, A1, A0, B3, B2, B1, B0. So, W4, I have got A is nothing but A3 dot A2, A1, A0, B is nothing but B3 dot B2, B1, B0. I repeat, whenever I write this expression, these are binary. So, that time it is binary 0 or binary 1, binary 0, binary 1, all, and the arithmetic they employ is binary arithmetic. Here I cannot put a minus and all that, but the moment I take the decimal expression, okay, under the 2's complement system formula, there I can take them as decimal variables and do anything I want. All right. Now, so I am just simply apply the Horner's rule here for this example. So, A by D times B by D, this product will be what? Minus A times B3 plus 2 inverse A times B2 plus 2 inverse A times B1 plus 2 inverse A times B0. Okay, this is what I have. Now, let us start with A B0. Here this A actually A by D, okay, but I am not writing it, it is understood that is A by D, it is a decimal value. So, these values are actually A by D, but I am just not writing the by D part here. I hope you understand that in this is a decimal expression. So, wherever I write capital A, they are all decimal capital A. Similarly, B0, B1, B2, they are all decimal values, decimal digits. Okay. So, let us start with A B0, decimal A times into this into decimal B0, all right. But decimal A, this is again now minus A3 plus A2 into 2 inverse, A1 2 inverse 2, A0 2 inverse 3, this into B0, which is minus A3 into B0 plus A2 into B0 times 2 inverse, A1 into B0 times 2 inverse 2 plus A0 into B0 2 inverse 3. All right. Now, before I proceed further, let us see one thing. This is decimal expression. What is small a3 or a2, similarly b0? Okay. They are all originally they were binary bits. Now, in this they will be treated as decimal digits, but value remains same. Binary 0 means here it is decimal 0, binary 1 means decimal 1, so on and so forth. Now, let us see one property. Suppose I give you two binary bits a and b. Okay. If it is a by d times b by d, my claim is this is equivalent to, in binary domain, this is decimal domain, and in binary domain it is equivalent to and operation, this and of binary a and binary b. That is, if I do binary a dot binary b, whatever bit I get, its decimal value will be same as decimal of a times decimal of b. You can easily see, suppose a and b both are 0. Suppose a and b both are 0. So, a by d is 0, b by b is 0. So, left hand side is 0 into 0, 0 decimal. Here it is binary 0, but 0 and get 0 is the binary 0, its decimal value will be 0. So, that is satisfied. This is 0 and this is 0, satisfied. Suppose this is 0, this is 1, decimal value is 1, decimal value is 0. If decimal value of a is 0, that means in binary it is 0. If decimal value of this is 1, then in binary it is binary 1, and AND gate of them 0.1 is binary 0 and binary 0 is decimal value is decimal 0. So, decimal 0 on this side and 0 into 1 0 on this side. So, this is satisfied. Similarly, if this is 1 by decimal 1, this is decimal 0, if you multiply you get 0, but if decimal 1, here it is binary 1, if it is decimal 0, here it is binary 0 and 1 dot 0 is a binary variable whose value is logic 0, binary 0. So, its decimal value is again simply 0 only. So, this is satisfied, and last one, if both are 1, then 1 cross 1 on this side, but if it is 1, here it is binary 1, if it is decimal 1, it is binary 1. So, and 1 dot 1 is a binary 1, binary 1 has decimal value equal to decimal 1 only. So, again, so this side decimal 1, this side its decimal value is decimal 1. So, this is satisfied, which means if I give you two binary bits A and B in decimal domain, if you multiply their decimal values, decimal value means if it is binary 0 it remains as decimal 0, if it is binary 1 it remains as decimal 1. If you multiply them, it means in binary domain you treat them as binary bits and do an AND gate first, AND operation between them, whatever binary variable you get out of it, that is A dot B, that will have the same decimal value as the product of the decimal of A and decimal of B. So, in binary domain I simply have to represent that as A dot B, all right. That means, this is a decimal expression, this is corresponding to a binary word. What word? This is decimal bit, decimal digit, decimal A3 into decimal B0. In binary domain it will be binary A3 dot binary 0. This will be, here it is decimal A2 into decimal B0. In binary domain it will be A2 dot B0. I am just first writing them. Similarly, A1 dot A1 decimal A1 decimal B0 product, it will be binary A1 dot binary B0, and then A0 cross B0, A0 cross B0 means binary A0 binary B0. And if I put them side by side, I get a 4-bit word. What will be the decimal value of this? Under 2's complement formula, it will be, this will be treated as a decimal digit. So, it will be decimal A3 into decimal B1, decimal B0, okay, decimal B0 with a minus sign. So, it is already there, plus 2 inverse times. So, 2 inverse decimal of this will be A2 decimal into B0 decimal is there into 2 inverse, plus A1 dot B0 in binary domain. In decimal domain it will be decimal A1 times decimal B0 present into 2 inverse 2, plus again it is A0 dot B0 in binary domain. So, in decimal domain it will be decimal A0 times decimal B0 into 2 to the power minus 3, that is what I have here. So, any A times B0, decimal value of A into decimal B0 will give rise to a 4-bit word here. It will be just like this, if A is capital A, so A3 dot B0, A2 dot B0, A1 dot B0, A0 dot B0. So, that is what I have, okay, here. So, start with A B0, capital A B0 means if I form a table, A B0 means a 4-bit word, A3 B0, A3 B0 means A3 dot and operation. Dot I am just dropping, it is there. If you want, I can put also A2 dot B0, A1 dot B0, A0 dot B0, all right, the 4-bit word. But this is to be multiplied by 2 inverse, this decimal value to be multiplied by 2 inverse, which means in corresponding binary word, what will happen? Everybody will get shifted to the right by 1, and this is the MSB that will get, there is a sign bit, where there is a binary point here, there is a sign bit that will get extended. So, I should shift them to the right and extend it, but I can jolly well do this way also. I put the binary point from here to I move here and extend this. Okay, I will get the same thing, you can easily verify. A3 B0 should go to the right of binary point and again come back. So, it has gone to the right of binary point and again come back. A2 B0 was just to the right of this, it will be shifted further. So, binary point here, so it is shifted further and everybody shifted further. And this guy has gone out of my register because register is 4 bit. This is what I have. So, there is 2 inverse AB0. Then AB1, same logic again, A3 dot B1, A2 dot B1, A1 dot B1, A0 dot B1. You add. Whatever you get, this is called, I get some intermediate result, that is called partial product, PP. PP first stage, first PP. So, there is a PP1, but it is the LSB. You add the two, incoming carry is 0 to the odd adder, result is here, that will generate a carry and that will move to this side. So, this carry plus these two will be added, that will give rise to a result PP1 next bit, and again a carry will move to this side, this will be added, that will give rise to PP1 but second next bit, and they will get added. Okay. So, you have PP1 3. Okay. This will be this result. Then this has to be multiplied by 2 inverse. So, my binary point was here and this should be shifted to the right by 1 and then this should come back here. You can as well move the binary point to this side and we extend this and become 5 bits. So, LSB it is chucked out. So, you got this result. That is this summation. Now, again multiply by 2 inverse means, sorry, now it is this much. Now, AB this is AB2, this is going to erase AB2. So, AB2 means again a binary what? A3 dot B2, A2 dot B2, A1 dot B2, A0 dot B2. So, A3 dot B2, A2 dot B2, A1 dot B2, A0 dot B2. You add the two, incoming carry is 0. So, this is partial product of the second next stage. So, stage number 2, 0th bit, carry generated moves here, these 2 plus carry, this will give us to new bit PP2 1, again carry moves to this side, these 2 plus carry, it will be PP and carry moves to this side, PP and that is all. And then 2 inverse times that. So, there is a binary point here, instead of shifting everything to the right, I move the binary point to the left as before and this is PP 3 2, this guy comes here. Unfortunately, I do not have space here. So, next one is minus A into B 3. Minus A into B 3 means what is minus A? In case of minus A, in binary word it will be complement each bit and add a 1 at the LSB. If I complete, that is, it will be A3 bar, A2 bar, A1 bar, A0 bar plus 0 0 0 1. There is a binary point here and these together to be AND gated with B3. So, I will take AND gate of this part with B3 and AND gate of this part with B3 and add. If I add AND gate of B, this will be A0, by the way, first let me erase this, let me, this chucked out. So, it will be A3 bar B3, this B3, A2 bar B3, A1 bar B3, A0 bar B3, the dot gate. And then again here 0 dot B3 is 0, 0 dot B3 is 1 dot B3. So, only B3 will come here. You add, you get the result. Okay. So, this is usage of Horner's rule. Now, the question is, we have to develop a hardware. So, what is the dependence graph here? You remember in the very early part of this course, I said that there are three graphical representations. One is called signal flow graph, one is called data flow graph, and the other one is dependence graph. Okay, dependence graph. So, what is the dependence graph of this? This I will consider. This is a big thing. So, I will not start that here. I will consider in the next class. Thank you very much.